Over the past 350 years, scientists have discovered and characterized more than 100 different elements. Of course, metals like gold, silver, copper, and lead were known since antiquity. But the first scientific discovery of an element was in 1649, when Hennig Brand discovered phosphorus. By the mid-1800s, about 60 other elements had been isolated, and scientists had noticed patterns of chemical behavior that led them to put similar elements into groups, first in triads, or groups of three, but later in larger groups. It was Dmitry Mendeleev, a Russian scientist, who put all of this together and published what was then a comprehensive periodic table of elements. To see how this works, we will assign each element to a block, and then we'll assemble the blocks into a table. Our blocks will indicate the atomic number, which is the number of protons in each atom of that element, a symbol for the element, which will make it convenient to write the formulas of compounds, the name of the element, and its atomic mass. Remember that the atomic mass is the average mass of each atom when expressed in atomic mass units, when averaged over the natural abundance of the isotopes. Hydrogen has an atomic mass that's slightly greater than 1, because a small fraction of naturally occurring hydrogen exists as the isotopes deuterium and tritium, which are chemically similar but have extra neutrons in the nucleus. Taking the first 10 elements in order of atomic number, we place hydrogen and helium into our table. Lithium is much more like hydrogen than helium, so we put it in the same column as hydrogen by starting a second row. We place the remaining elements in the second row. But now we notice that neon, element 10, is very similar to helium, element 2. So we create a break in the first row to move helium over to the same column as neon. The next element is sodium, and its behavior is very similar to lithium, so we start the third row of our table. Likewise, magnesium is like beryllium, and so we include it next. And we continue this way to complete the third row of elements in our table. The row ends with argon, which is an inert gas, so everything looks good. But now we need to shrink this down a little bit to create more room in our table to add the fourth row. Each of the rows so far starts with a highly reactive material and ends with an inert gas. The fourth row starts in the same way with potassium. Then calcium. But when we keep adding elements to this row, we don't get to an inert gas until we reach krypton, element 36. So just as before, we want to line up the elements with similar properties in columns so that we create a break and move the last 6 elements in rows 1 through 3 to line up with krypton. Adding elements to row number 5 goes smoothly all the way to element 54, which is xenon, and the properties line up nicely. As we look to add row 6, we must add 32 elements before we reach the next inert gas, which is radon. The first 2 members of this row, cesium and barium, are a good fit to the existing pattern. The last 6 elements are also a good fit, starting from radon and working backwards. Still working backward, we can fit everything from hafnium to mercury just fine. But we're left over with 15 elements to fit into one space, so we need yet another break in the table. Now, our table is getting pretty wide with all these breaks, so for convenience of presentation, we'll just include the 15 elements in a separate row below our table. And we'll include a placeholder that points to this extra row containing elements 57 through 71. We still have more elements to include, So we now start row 7 with francium, element 87. Everything goes smoothly, and we need another placeholder that points to an extra row containing elements 89 through 103. Notice, however, that row 7 is not complete near the end. That's because the elements that we know will belong in this row have not yet been discovered and characterized. This really is the discovery zone. When we constructed this table, we intentionally lined up elements with similar properties in columns, and we have named some of the columns to define the groups of elements. For example, the first column of elements is called the alkali metals. They are all metals except hydrogen, and they are all extremely reactive reducing agents, which means that they tend to give up electrons in chemical reactions. The second row contains the alkaline earth metals. These elements are somewhat like the alkali metals, but are not as reactive. On the far right-hand side of the table, the last column contains the inert gases that we used to end each row. These are often called the noble gases because they aren't completely inert, but they still are very highly unreactive. Next come the halogens. This group of elements is highly reactive, but unlike the alkali metals, the halogens are strong oxidizing agents, which means that in reactions they tend to take electrons away from other elements. Sometimes the first 2 and last 6 columns are combined to form the so-called main group elements. This includes the full range of reactive behavior from strong reducing agents to strong oxidizing agents to highly inert elements. The elements in between are called the transition elements. That's because their properties change gradually with increasing atomic number along each row. The 2 extra rows at the bottom are called the inner transition metals. These 2 rows are further classified as the lanthanide series, which includes elements 57 through 71, and the actinide series, which includes elements 89 through 103. You may have noticed that nearly all of the elements on the left-hand side of our table are metals. In fact, every element on the left side of the table is a metal except hydrogen. In contrast, the non-metal elements appear in the upper right side of the periodic table. Hydrogen is also included in this group. The metals and non-metals are separated by a small group of elements that are appropriately called metalloids. That's because they have properties that are intermediate between metals and non-metals. This group of elements forms the basis for nearly all kinds of modern semiconductor materials. Almost every list of chemical elements is presented in this special way that was invented by Dmitry Mendeleev, because the spatial arrangements of elements emphasize the commonalities of their chemical properties. The table also provides important clues to how the electronic structure of atoms influences their chemical behavior. That will be the subject of another video.